Have you ever wondered how the electric motors that keep most of modern industry running are built? Behind each of these devices lies a meticulous process that transforms steel sheets, copper wires, and mechanical parts into machines capable of converting electricity into continuous and precise motion. We will explore how millions of electric motors are mass-produced, following their journey from raw materials to final assembly on the test bench. Electric motors are responsible for powering over 90% of the movement in modern industry. If these machines were to stop, countless processes would immediately grind to a halt. Despite their importance, most people have never had the opportunity to closely observe their inner workings. Manufacturing one of these devices is an extremely precise and highly specialized process. The basic structure begins by stacking extremely thin sheets of electrical steel, each manufactured with tolerances of just a few hundredths of a millimeter. These layers are grouped together to create a perfectly uniform magnetic core. Then, copper is wound in specific patterns that ensure each coil carries the correct voltage. Added to this are the central shaft, bearings, and cooling systems, which work together with a coordination similar to that of a biological mechanism. To understand this entire process, we analyze everything from raw materials to a fully assembled engine, tested on a specialized test bench. These machines not only represent a significant achievement in modern engineering, but they are also fundamental components in virtually every existing manufacturing industry. Millions of units are manufactured each year, from small motors installed in household appliances to powerful industrial equipment used in mining, metallurgy, and renewable energy. The global electric motor sector has already surpassed $150 billion and maintains a steady growth trend due to process automation and the increased use of cleaner energy. What is most impressive is how these machines manage to convert electrical current into stable and continuous motion. When energy reaches the stator coils, it generates a rotating magnetic field that, in turn, induces current in the rotor, causing the shaft to rotate smoothly and precisely. For this movement to be possible, the first thing that must be manufactured is the stator core. This piece, made of steel with special magnetic properties, acts as the foundation for organizing the internal electromagnetic field. Although from the outside it appears to be a simple circular metal structure, creating a homogeneous and precise core requires an automated manufacturing system with extremely rigorous controls. The process begins with the stamping of thousands of thin sheets of magnetic steel. Each sheet has a minimal thickness and is coated with special insulation that prevents energy loss caused by eddy currents within the material. These are not simple discs, but rather pieces with a complex design that includes narrow grooves where the copper coils will later be inserted. Because these grooves must align perfectly, the sheets are shaped using high-precision equipment that allows for virtually no margin of error. Instead of heating them, which could deform them, they are compacted by applying considerable pressure, forming a solid cylinder without affecting their magnetic properties. After this, each slot receives an ultra-thin insulating coating made from materials such as polyester or high-performance fibers like Nomex. This insulation prevents direct contact between the copper and the steel, ensuring complete electrical protection. Specialized robots carry out this entire process, as even minimal misalignment could cause a short circuit once the motor starts running. Much of the motor's efficiency, from its magnetic capacity to its rotational stability, is determined within this core. With the stator now assembled, a stage begins that marks the functional birth of the motor, the installation of the coils. Before inserting any wire, each slot must be prepared with a heat and electrically resistant insulating sheet, which acts as a buffer to prevent electrical leakage and protect the copper from metal-to-metal contact. This step is essential to ensure the wire can be positioned precisely without risk of future failures. The copper wire used is enameled, which adds an extra protective layer. This material is automatically fed from high-speed winding machines. Although these machines can work quickly, the real challenge lies in how each turn is arranged. The coils must lie perfectly flat within the slot, without crossings or knots, and under constant tension. To achieve this uniformity, automated systems pre-read each slot, calibrating the exact way each wire should be positioned. In large industrial motors, each slot can accommodate dozens of turns, arranged in neat layers. Once the winding is complete, the ends of each layer are temporarily clamped to secure everything until the final connections are made. Only when the copper arrangement is geometrically precise can the motor reliably conduct electricity and convert it into precise mechanical motion. Once the coils are in place, a crucial phase begins to ensure the motor's safety and durability. The insulation and heat treatment of the entire assembly during operation. Electrical currents generate heat, which can cause vibrations, displacement, or premature wear. To prevent this, technicians manually secure critical points using special heat-resistant wires. These ties hold the coils firmly in place without deforming the core. Next, the entire stator is immersed in a tank of liquid insulating resin, usually industrial epoxy or polyester using vacuum or electromagnetic immersion techniques. The resin penetrates between each thread and every internal cavity. Once hardened, it becomes a rigid block that protects against moisture, vibration, high temperatures, and other factors that could affect the motor's performance. Only when this structure is completely sealed can the next stage begin. With the stator completed, it's time to build the rotor, the part responsible for rotating and generating actual movement. As with the stator, sheets of electrical steel are used, meticulously stacked to form a compact cylinder. These sheets also have an insulating layer, since the magnetic behavior requires the same precision as in the stator. After stacking, they are subjected to a hydraulic press that compresses them into a rigid core that will soon function as the heart of the movement. However, this core alone cannot rotate until it is mounted on a metal shaft, which is the component responsible for transmitting force to the external machinery. The shaft is manufactured from high-strength steel, designed to withstand constant mechanical stress. First, the base material is cut and then fed into a CNC lathe, where automated tools trim, polish, and shape each section according to an extremely detailed design. Every surface must meet strict tolerances and have a smooth finish to prevent future wear on the bearings. Once the shaft has been verified through precision inspections, it is joined to the rotor core. To do this, the shaft is gently heated, allowing it to expand. Under the controlled pressure of a press, it is inserted into the rotor. As it cools, the shaft contracts and becomes completely fixed without the need for welding or adhesives. This thermal bonding ensures stability even at high operating speeds. The next crucial component is the bearing, a fundamental part that allows the rotor to turn smoothly and without excessive friction. Bearings are slightly heated before installation, which facilitates their expansion and ensures a perfect fit on the shaft ends. Once they return to room temperature, they are firmly secured in place, creating a safe interference fit. With the rotor and shaft ready, the outer casing is manufactured to protect the entire internal assembly. The process begins with steel sheets that are bent into a cylindrical shape. These pieces are then pressed to achieve their precise geometry. Cooling fins are subsequently welded on to help dissipate the heat generated by the motor during operation. The surface is carefully inspected for imperfections, and then an electrostatic coating is applied to protect it from corrosion and wear caused by demanding industrial environments. Once all the components are ready, final assembly begins. The stator is inserted into the housing, while the rotor is positioned using alignment tools that ensure the shaft is perfectly centered. The space between the rotor and stator is extremely small, so any misalignment could lead to failure or loss of efficiency. Each part is checked and adjusted to guarantee absolute precision. With the mechanical components now complete, the technicians focus on the electrical connections. The stator wires are organized, insulated, and connected to specific terminals inside the motor. All the wires are neatly arranged and secured to prevent movement caused by vibrations. The main cable is routed safely through the motor housing. Before the motor can be considered finished, the outer casing undergoes a controlled application of protective paint, ensuring precise thickness and adhesion. A metal cover is installed on the back to prevent accidental contact with moving parts. Finally, an identification plate is affixed, displaying technical data, serial number, and a QR code for tracking and documentation. Finally, the motor reaches one of the most important stages of the entire manufacturing process, its evaluation on the test bench. Here, the complete assembly is placed on a stand specifically designed to analyze its behavior under controlled conditions. Advanced sensors record multiple operating parameters including power consumption, the intensity of vibrations generated by the rotor's rotation, the noise level emitted by the unit, and its performance when operating without a connected load. Each of these data points is essential to determine whether the motor meets the established standards for its category and power rating. When current is applied to the stator, it generates a magnetic field that sets the rotor in motion. From that moment, the entire system begins to rotate while instruments capture real-time data. Technicians monitor graphs, performance curves, and instantaneous readings to ensure there is no abnormal behavior, such as irregular current spikes, unusual noises, or vibrations exceeding permissible levels. Once the automated tests are complete, a final manual inspection is performed. At this point, specialized technicians carefully check the smoothness of the shaft's rotation, ensuring there is no abnormal friction or misalignment. They also check the firmness and stability of the internal electrical connections, verifying that each terminal is properly tightened and that the insulation is undamaged. Furthermore, they confirm that the nameplate, serial number, and other informational elements match the production system records and are installed on the motor without defects. Thus, what began as simple sheets of steel, copper wires, and shapeless metal parts is transformed into a machine capable of converting electrical energy into constant and precise motion for thousands of hours. The complexity of this process, which combines engineering, automation, and rigorous controls, demonstrates the level of accuracy required to ensure that each motor can perform reliably, even in the most demanding industrial environments. Each unit represents a final product resulting from multiple stages where precision is paramount and where every detail directly influences its durability and performance.